Okay, let's continue. All right, so now in this next chapter, we'll go over work and energy. So what work is and energy is. So work, when we talk about in physics, the quantity work is very well defined. It's not like what we think of work when we use everyday vernacular. Work has a specific definition. And work is basically how much, how can I describe it? It's basically what you get for the force that you apply, right? Like I said, well, like we've been going over, you could have two forces that counteract each other, right? And it doesn't move the object, right? If I'm pushing against my hand, right? You can't tell, but there's a force being applied on my two hands. I'm actually using energy to push my hands together, right? And nothing is happening, right? It's no longer moving. We would say that the forces associated with pushing on my hand does zero work. It doesn't do anything to the object. It doesn't move the object. And the way we define work is how much we move an object for how much force we apply. So a good image of this is, let's say if we're pulling a crate a certain distance. So let's say if we have a crate, right? And we're dragging it along the floor, right? We're pulling it along, right? And we move it to over here. Right? We move it this distance, D. Right? Now, the work that I do to move it from here to here is equal to the force I apply along the direction of motion. So it's the force that's perpendicular, that's parallel to the motion, and that's D. So if I pull this object from here now, if I'm over here, it's a lot harder for me to pull it, right? Because of the angle. The angle is not optimized, right? But in the end, I do the same amount of work. Even though I apply more force like this, I would do the same amount of work, right? So work is the end product. How much for the force that I use, how do I move these objects in the universe, right?
So when we calculate force, we only take into account the vector of force, which is parallel to the direction. That's what it is.
Yes, it's the force parallel to the direction. So
or the component of the force, which is parallel to the direction.
Well, yes, it's the component. It's the part of the force that's parallel. It's the component. Yes. Right. So if this is F, then the force that's parallel to the distance that we move would be cosine, right? So it would be cosine F times D. Right? So if I want, let's say if D is equal to 40 meters, this is equal to 37 0.2 meters, and F, call it FP, is equal to 100, right, newtons. How much work do we do by moving the object from here to there? Well, we'll just plug it in, right? It would just be the work that we do, the work that the person does is equal to the force times cosine theta d, right? And in this case, the force along this direction is just the person moving, right? So be 100 times cosine theta times d, or times 40. Right? And that is equal to 3,200 joules. Joules is the energy, is the units for energy. And it's defined, joules is equal to Newton meters, Newton times meters, right? It's just force times the distance. Okay. Now, if there's friction, right? Let's say if there's friction here, that's doing opposite work, right? That's doing what we call negative work. It opposes the motion, right? So if it's going this way, we would get a negative number, right? And what we find, let's say if our frictional force is 50 newtons, let's say FR is 50 newtons, that means the work due to FR is, right, well, we know that FR times cosine times the distance x, d, we'll call it d, times, what's the angle now? Well, this is 37 degrees, 37.2, or 37.
Should be.
It would be 180, right?
Oh.
Because friction is the opposite direction of the motion, right? So this would be 180 degrees, right? And what is cosine of 180? -1, right?
1 or 0.
-1.
Negative.
So that means that we get -50 times 40, right? Which is 2,000, -2,000, right? So this is the work that we do on the box. This is the work that friction does.
But the work that friction does, which distance do we use in calculation?
Well, we use D. The box, so the box moves, the box moves 40 meters, right?
Mhm.
The total work done is the sum of all the work,
Mm-hmm.
right? So that the work total is equal to the sum of all the components. And I apologize for the contrast. My marker's dying. Right? And, right? So that means if we want to calculate the total work, we would do this for this problem, right? There's only two forces here. The pulling on it, and then the frictional force. Or I should do addition and then addition, and then it would, and then we just add in the minus sign. Here. -2. Right. So what we did was we calculated the work for each separate force, and then we added them together. This is the same thing as if we calculated the total net force along this direction, and then use that total net force to calculate the total work done on the system. It's the same thing, right? Here I calculated the work for each force, and then added it together, just to show you the different forces, and then, or we could just do the total net force along the direction of motion, and then calculate the work. Okay. Now, in general, when we want to calculate the work, so let's consider another easy problem. So let's say if we want to climb a hill. Right, and it's h meters to the top of this hill, right? And we have a backpack on that we're carrying up the hill, right? Let's figure out the work done to move pack to top of the hill. So let's calculate the total work done to move this pack to the top of the hill up here. Right. So what do we do first? Well, we do something similar to what we've done in the past. We do a free body diagram, right? And this hiker, assume this hiker travels at a constant velocity. V is equal to a constant, right? So if he's walking at a constant velocity, right, what are the forces on this backpack? So what are the forces on this backpack if he's walking up this at a constant velocity?
Got the normal force that he's holding it?
Yes, that's correct. We have the force of the hiker pushing up on the backpack. What else?
Gravity?
Yes, and we have gravity. That's correct. mg. Right? So in the y direction, right, and the forces in the y direction is equal to the acceleration. What's the acceleration if he's moving at a constant velocity?
0.
0, that's correct. And this is just equal to, right? So we find that f of h is just equal to mg. And in this case, the backpack is 15 kilometers, 15 kilograms. And then h, just to write it down, is 10 meters. Right. So using this, the force, the normal force is 147 newtons. So this is the force that the person applies to the backpack, right? Now, the question asks, determine the work a hiker must do on the 15-kilogram backpack to move it up to the top, right? So how much work does the person have to do, right? Our work formula is given by the parallel force times the distance that it moves, right? So what do we use as the parallel force and the distance? What is the work done, right? Let's apply the same logic that we've been using in kinematics. Let's break it down into two coordinates, right? One horizontal and one vertical, right? Is there any work that he does associated with moving this way?
Yeah, the work is him picking it up and pushing it basically, or pulling it.
Well, what is the work? What is the explicit definition of the work? It's the force that's parallel to the motion. So if we're moving along this way, what would the work be? Well, we have a distance. We just need to know the parallel forces. Is there any parallel forces in this case on the backpack? Is there any force in this direction, in the horizontal direction?
I don't think so.
Well, let's look at the free body diagram that we drew. And any forces in this direction?
No.
No, he's moving at a constant velocity. And so he's moving at a constant velocity in this direction. So there's no force on here, right? On the backpack. So this is 0 in this direction. So there's no work done moving the package this way. Right? Because he's just moving at a constant velocity. There's no force applied. The only force is upwards, right? Or vertically. So what is the D that he moves vertically? Just H, right? And then the force that the person applies, what is that? That's FH, right? So, and this is all in the vertical direction. So this FH force is totally, is completely parallel to the equation of motion. So we could just write that. So the work he does is just equal to this, which is equal to mg times h. All right. Now this says something really, really cool, right? You don't realize it, but it doesn't matter how much he travels in this direction, even though you think he does, and from experience, it takes more work to travel along this direction, right? But this is because of dissipative forces, right? The fact that whereas we're moving, we're kind of not going at the same velocity the whole entire way, and there's also air drag, and there's all these other phenomena that comes into play. But in the generalized sense, if there's no forces in this direction, we don't do any, there's no work done along here. So it takes the same amount of work to go up the ramp or to lift it up by elevator, right? In a perfect world, in this idealized case, right? That's pretty amazing. All that matters is the height that you travel up and down. Doesn't matter about the slope of this ramp.
So the angle does not matter?
The angle does not matter. Let's look at our final equation. It's just the height. Right? It's very, very simple. Right? How much work I have to move up the package. It actually doesn't matter how we move. If we move up and down like this. Why? Because when we're moving down, it negates the force that as we're moving upward. We'll get to that later. But so in the end, it's just about the displacement in that direction, right? So now, so if we calculate it, right, it's 147 newtons times 10, so it's 170 joules, right? Now, that's the work done by the person. What is the work done by gravity? Well, let's write it out. You know what? I want to explicitly write out the angles here. Here, we're traveling in the same direction as this displacement, so the angle is 0. So we just left with HD, and then when we plug it in, we get our answer. Right. For gravity, right? We have to figure out the force parallel, so it's just Fg, and then what's the angle? So if gravity is pointing downwards and our displacement is upwards, what would be the angle between the vector and the direction that we move?
180.
180, that's correct. Right. And then we get the same quantity, just in the opposite, negative work. So what's the total work done on the package? Or I shouldn't say the total. What's the net work done? What do we do? The net work is just, we just sum it up. And when we sum it up, what do we find? It's 0. So the work that we put in, that we exert to move this package up, is negative work by gravity. So whatever we put into the package to move it up, it's taken away from it's taken away by the work done by gravity. Right? But even though the net work done by all the forces is 0, and that makes sense, right? What is the net acceleration? It's 0, right? The velocity is constant, so there's no net force, actually, right? So there's no work done in this situation because there's no net force. So, but that doesn't mean we're not doing work. We're transferring the work. We're taking work from our body, or the energy from our body, and we're putting it into what we'll see is the gravitation, is energy stored in the gravitational field, or this idea of gravity. And this will become very important later on. So before we continue, I want to go over something else. So I want to go over a scalar product. So I want to go over a scalar product. So work is not a vector. Work is a scalar quantity. So you can add how much work you do in the y and how much work you do in the x to get your net work, right? And what we use to calculate work is called the scalar product. So what happens in this case, or if we think back to that box that we moved in the first case, right? What ended up happening was we had our force vector, and we had our displacement vector, right? The displacement was in one way and the force was in another way, right? And then we had to find, to calculate the work, we had to find how much of this force vector is along the displacement vector. Or how much do these forces, what's the measurement of how much it's a measure of how much these two vectors are in the same direction, right? And there's a specific way to calculate this mathematically, and it's called a scalar product or a dot product. And the dot product is described by this. So it's two vectors with a dot in between each other, like that, right? And what this ends up being equal to is the magnitude of each vector multiplied by the cosine. So in general, if you have two vectors, you want to see how much of these two vectors are in along the same direction, right? It would be given by this, right? If the force vector was completely perpendicular to the displacement vector, this would be 0. None of it is along the same direction. If it's going the opposite way, that means it has a negative correlation, right? If D is this way, then I'm going in the opposite direction. If it's perpendicular, there's no relationship. So this is 0, right? And generally, work is given using this formula. Work is given by this. Right? It's the same formula that we had before. It's just more generalized now. Right? And this is one way to calculate the vectors, right? This is the way to do it. If you're given the angle and the magnitudes of these two vectors, you would use this equation. If I gave you explicitly what each of these vectors were, right? So if I gave you each of these vectors, right, let's say if I had f is equal to fx I plus fy j plus fz k. Let's say if I actually gave you the components of each one of these vectors, right, and then d would be this. Okay. If I give you this, the way you would calculate the dot product is very easy. What you would do is you would multiply these two components together, and then you add all these up. So this would be fx times dx plus right, and you just multiply the two components together and you add them all up, right? And this makes sense, right? If you multiply the two components together, that kind of gives you a measure of how much of these two vectors are along the same path, right? And you multiply it together, you add all these up. And that's the general formula for how you do a scalar product. So it converts two vectors into a number. This is a number. This is a scalar quantity. Okay? Now, this sets us up for a situation where what happens if the force vector and and the displacement vector are never along the same path. Let's say if, we have that hill again. Let's say if we're going up the hill, and the hill looks like that, but none of my markers are. Let's say if we have a hill like this, right, where the force of our, the force that the hiker applies is always vertical. The displacement is never only just vertical, right? It changes, right? And using this dot product, we could add up the work done for each one of these segments. We break it up into small segments, and we calculate the work done at each segment, right? And if you look, right, so let's say, let me redraw it. Let's say if it's like this, right? So that means that we calculate the work done over here in this segment, and we calculate it over here. So for this, we approximate the angle using this, right? So we have F cosine theta I, right, for this section. And we approximate it over here. We add it all up. And then we add up the work done in this section. 2, let's say, and then we add it up over here. And we continue on and so forth, right? This turns into an integral. What we end up getting is this integral for the work. So instead of D, we're going to call each step that we take. So if we expand this, each step that we take forward, we'll call DL. So each one of these steps is DL instead of D. We'll call it DL. So what we do is we calculate the work for each one of these little segments, and then we add up the network for each one of these segments, and we get the total work done from A to B, to move something from A to B, right? And when we make these little segments infinitesimally small, we can do an integral and say that it's equal to it, because we no longer have this error associated with it, right? So this is the general formula. If the force changes along the way, and if the angle to the displacement also changes, what we do is we add up all these little work segments together, and that's what this integral really represents. It's a sum of all these little work segments added up to each other. And then we use this integral to calculate the work. And I'll stop here. And I'll post a video for the rest of the chapter. So, well, we did 10 minutes extra. Yeah. Okay. And then, so I'll finish this chapter, and I'll post the video online for it. I think I still have to post The Tuesday's lecture, I think I didn't post that. Is that correct?
Yeah.
Okay, I'll post that today. And then let me write down what needs to be done. Hold on, guys, before we finish.
And don't forget about the questions, the 2 questions you're gonna.
Yep, exactly.
All right, Professor. Enjoy your day.
You too. Take care. Okay. So post Tuesday lecture.